Hello students, in this video I'm going to take you through the um, the justification for using Fourier series to express the solution of this initial boundary value problem. It's really going to come down to um, satisfying this initial condition. All right, so in a another video, one that you should probably watch before this one, I give an intuitive introduction to this initial boundary value problem, and we call it the heat equation. I say it's a temperature profile, and if the temperature profile is above zero, then it's clamped down at the boundaries and insulated, so that means it's going to decay down to a steady state and everything is going to go down to zero. So that's like the hot cup of coffee cooling down to room temperature. And if the initial temperature is below zero in the middle, but it's clamped down at the boundaries at zero, then it's going to heat up until it reaches the steady state of its surroundings, and so it'll reach up to the boundary conditions being zero. So that's like the cool drink warming up to room temperature. Um, all right, so what we want to do here is what if we had a solution to this boundary value problem? What's it going to look like, and how's it going to behave? So you notice, well, you may not notice, but I'm telling you that this function with this exponential multiplied by the sine satisfies the boundary value problem. I'm not going to say anything about the initial value, the initial condition for the moment. We're just going to focus on the boundary value problem. And the initial condition will require a series actually to construct f of x using a bunch of these, a linear combination of these UNs. I'll speak to that in a few minutes. And that series is actually going to be called the Fourier series. All right. So let's first show that it satisfies the boundary value problem. Notice that the PDE, the partial differential equation, the PDE, can be written as the derivative of u with respect to t minus the second derivative of u with respect to x equals 0. So I just push the uxx over to the left-hand side. Now, if I differentiate un with respect to t, then by the chain rule, the minus n pi l over l squared drops down, and I just leave the sign alone, and we get the exponential back. All right. If I take two derivatives of the solution, now remember, the first this will not get touched. This term will not get touched by the spatial derivatives, the derivatives with respect to x. Only the sine term will. The first derivative of sine is cosine. The second derivative is minus sine. And every time I take a derivative, an n pi over l pops out. So I'll have two of them for the two derivatives, and I'll have an n pi over l, and then a minus sign pops out because I'm taking the derivative of the cosine and I get the minus sign. So I get an n pi over l quantity squared, and you're starting to see that these two look very much alike. So that's where you get the balance of the two equal to each other. And so if I subtract du dt minus the second derivative of u with respect to x, then that minus sign changes to a plus, and I get the identity 0 equals 0. Or you could just use this PDE here and see that these two solutions happen to equal each other. So it does satisfy the boundary value problem. It satisfies the boundary conditions, and you can see that if I plug in 0, I get sine of 0, 0. And if I plug in L, then the L's cancel, and sine of n pi, because n is an integer, equals 0. Okay. Now, the PDE is satisfied. The boundary conditions are satisfied. What about the initial condition? Okay, notice that if I multiply if I the solution by some constant, let's call it Cn, then it also satisfies the PDE and the boundary conditions. Okay, so multiplying by a constant did not change the behavior of the solution. So since that constant is arbitrary, I can also add all the solutions together, and they would still satisfy the PDE and the boundary value problem. Because if each one satisfies the PDE, then the sum of them will. So what about the initial condition? Well, the initial condition says that if I plug in t as 0, I should get f of x. It's all spatial. Well, that implies that if I plug in a 0 here for t, that becomes 1. So I have cn times sine of n pi over lx, and that is supposed to equal f of x. So what we have here is that f of x is expressed as this infinite series, and that is called a Fourier series expansion. In fact, this is a Fourier sine series expansion of f of x. Now let's take a moment to notice something about the behavior of these solutions, and this goes back to our intuitive introduction of the solutions. Notice that this solution, as t goes to infinity, so if you take the limit as t goes to infinity, that does not touch the sine expansion here. This exponential is decaying, and our solution is going to go to 0. So that means it's going to go to a steady state as t goes to infinity, and it's going to want to satisfy the boundary conditions. So that means it's either going to warm up or cool down depending on what the initial condition is. Notice also that even as a full-blown infinite series, this solution will still satisfy the boundary conditions, because if you put in x as 0, then all the signs are going to be 0, and if you put in x as L, then you just get a bunch of sine n pi's, and those are still going to be 0. The question comes in, under what conditions of on f of x can we write that as a infinite series? We have to know whether or not that infinite series converges, and that's going to depend upon the coefficients, the CNs, and how we construct them or choose them. And that's a topic for another video. But anyhow, the thing that I wanted to point out here is that we're going to start seeing solutions of these partial differential equations and these initial boundary value problems written as these infinite series, and these infinite series are called Fourier series. Okay? So in future videos, subsequent videos, we're going to study the behavior of these Fourier series, and then eventually we'll construct solutions. We'll come up with a technique for constructing solutions to these initial boundary value problems that will look just like these. So you'll learn how to solve these initial boundary value problems and write these solutions for yourself. All right, good luck.